Where's going to problem? Take me a problem, Peter.
Okay, cool. All right. So you guys all know this. Newton's third law. For every action force, there's an equal and opposite reaction force. Anytime, anywhere in the universe, two objects interact with each other, they exert forces on each other that are both equal and opposite. Okay? So please make sure that you understand that every time you talk about a force, you need to make sure that you identify both the object doing the pushing or pulling and the object being pushed or pulled. Okay? A lot of times I'll have people they'll say like, oh, well, the wheelbarrow's force. And I don't know if they mean the force being applied onto the wheelbarrow or if they mean the force of the wheelbarrow pushing some other thing. Okay? So please make sure that you are explicit in describing forces this chapter, you guys. It's very, very important anytime you're talking about third law. Okay? Everybody good with all that? All right. So this all is stuff you guys have seen. I think we've talked about all this. I think that's good. All right. Couple quick important things to just remind you about. All right. First of all, if your action force is a push, then so is your reaction force. And if your action force is a pull, then so is your reaction force. Okay? So if I pull Zach, then Zach pulls me. If I push Zach, then Zach pushes me. Clear? Yep. All right. Couple weird ones. Remember, gravity is a force that pulls. Friction pushes. Okay? Yeah, because like if you imagine rubbing two pieces of sandpaper together, what are sand bits doing to each other? Are they pushing each other or pulling? Pushing, right? So same thing, except they're molecules instead of sand bits. All right. Action and reaction occur simultaneously. All right. Please don't think that it's like the two things are having a fight and Hecker pushes Zach and then Zach pushes Hecker. You know, that's not what's going on. They occur at the same time. Good?
Yes.
All right. Don't forget that it doesn't really matter which one's the action and which one's the reaction. Please make sure you understand. Oh, I forgot to put that question on that test. My honors test. Darn it. Please remember. Oh, wait. No, it is on it. Never mind. Okay, sorry. Please remember the action and reaction forces are always equal.
Wait, is that the test she's taking right now?
Yeah, I was realizing that, but she'll get an A anyway, so I'm not too worried about it. So, all right.
You got this.
All right. So remember, the action and reaction forces are always equal. Okay. So when I drop this pen, is there more force? Well, so somebody describe to me the action when I drop the pen.
Earth pulls the pen.
Earth pulls the pen down. The reaction is pen pulls the earth up. Which force is bigger? They're equal. Why does the pen move more?
Less mass.
Less mass, less inertia, right? Technically speaking, I just moved to the earth, right? When I drop this pen, I am pulling the earth up, and the earth does move a teeny, how many teeny weeny bit? Okay? All right? Why don't we notice the earth moving? Gigundous mass, relatively, whatever normal size force, the acceleration is going to be so close to zero that we'll never notice it. Good? All right. So last year in my class we did the if everybody jumps calculation. We don't have time to go through it right now, but it turns out even if everybody jumps, it's not enough force. Okay? All right. All right. If you want, go back and watch my honors third law video, and I do the calculation in it. You're happy to welcome to go back and watch it. All right. Finally. Didn't occur to me that we were doing this on the same day she was taking this test. Finally, this. I'm going to let you read it, because there's that exact question is on the thing.
This is very, I got organizational skills.
All right. Does this ring a bell, you guys?
Yeah, from that honors test last year.
Okay, right. Yeah, well, it's not yet. All right, good? All right. So we can talk about that more later if we need to. Okay. Do we need to run through these examples? If Hecker pushes Zach, Zach pushes Hecker, Pen pulls Earth pulls Pen.
Not much. Yes.
You gonna do? Okay, sure. So here's a good one. So imagine a helium balloon floating away. Okay, so the helium balloon floats up, eventually it bumps into the ceiling, right? So somebody describe for me action force. Sure, go ahead, Margaret. Balloon pushes the ceiling up. Good. Make sure you include a direction. And the reaction would be, sure.
The ceiling pushing the balloon down.
Ceiling pushing the balloon down. Good. You got to make sure you identify the two objects. All right. We talked about the baseball player sliding into base, right? That's like a common example that comes up, right? So why doesn't, when you slide into base, why don't you keep moving forward? Because of friction between the player and the ground, right? So who wants to describe for me the action? Sure, we got you.
You push the ground like one way.
Well, which way?
Like base.
Oh, okay, good. The direction you're running.
Yeah.
Right.
Where you're going, and then the ground pushes you the way that you're not.
There you go. Everybody good with that? Okay. Cool. Margaret, you good?
Nope. That's not the way.
Margaret, you good?
Yes, I just really hate this concept.
Okay. Sorry.
It makes sense.
All right. Everybody set? Okay. So there's a whole bunch of them here. It would be worth your while to go through and just kind of make sure you understand all those. And if you have questions, grab me. All right. So. Oh. There we go. All right. So let's do this first example. All right, so we got Roy and Sally standing on frictionless skateboards. So let's draw this. So here we go. Here's Roy. Here's Sally. Okay, so in the problem, Roy has a mass of 80 kilograms. Sally has a mass of 60 kilograms. Sally pushes Roy. So to draw Sally pushes Roy, I'm going to draw an arrow coming out of Roy because he's the object being pushed. I'm going to put the arrow in the direction he's being pushed, and then I'm going to label it according to what is doing the pushing or pulling. So in this case, that's the force of Sally, right? Does this all ring a bell? All right, so let's see, that's 960 newtons. All right, and then similarly over here, if my action is Sally pushes Roy, then the reaction is Roy pushes Sally. Notice, depending on which way you drew it, one of those two forces has to be negative, right? So don't forget those negative signs. Cool? All right, and do we see why they don't cancel? If you look over here, nothing to cancel. If you look over here, nothing to cancel. Good? All right, so let's find our acceleration for each of them. So technically there are two other forces on Roy and Sally. We don't have to worry about them. What are the other two forces I haven't drawn? Gravity and normal force. They're frictionless, so we don't need to worry about it. So I think we're good. So the acceleration of Roy is the net force on Roy divided by his mass. So negative 960 newtons over 80 kilograms. Gives you what, negative 12, I think, meters a second squared. All right, and over here, acceleration of Sally is net force on Sally divided by her mass. So 960 newtons positive over her mass, which is just 60 kilograms, gives you 16 meters a second squared. All right. Sorry?
Can you flip the sign?
You could absolutely flip the signs, yeah. If you made your drawing the other way around, that's totally cool. All right, who accelerates more? Sally, why? Less mass, less inertia, right? All right, good? All right, so notice in this interaction, both objects move because there's only one force on each of the two objects, right? Okay, but that doesn't always happen. So example 2 is almost the same thing, but this time instead of having Sally pushing Roy, it's me pushing a filing cabinet. All right. So let's run through this real quick. So here's me. All right. And I'm going to push a cabinet. Oops. So mass of filing cabinet, it says, is 150 kilograms, right? So it's basically just this. So I'm standing at rest on a frictionless skateboard, and I'm going to push the cabinet. All right. So notice the cabinet there didn't move, right? How come? Even if it.
Skateboard friction was not necessarily the floor.
Yeah. So if we assume that the cabinet's not on wheels, what's going to prevent it from moving? You guess? Static friction, right?
The frictionless skateboard.
The skateboard is frictionless.
Oh.
Gotcha.
So if both surfaces were frictionless, could you exert any force?
Sure.
You could.
Yep.
Okay, yeah.
Right. Good. I need to get another. I have another skateboard, but the ball bearings and the other one aren't as good. It doesn't. The demo never works as well as I want it to. But. All right. So if you go through and draw this, so here's the force of Hecker pushing the cabinet. All right, but it's not going to move because of, you guys just told me, why not? Force of static friction, right? Presumably. Follow? Or maybe there's a wall behind it or whatever. Everybody good up to there?
Yep.
All right. Now, what about me? Well, if Hecker pushes cabinet, then cabinet pushes Hecker, right? Cool. And so now you can find the acceleration by just doing net force over mass. Does that give you a -6? And over here, the acceleration of the filing cabinet is 0 because the net force on the filing cabinet is 0 because of friction. Follow?
Yeah.
All right. Any problems with this? Is this all ringing a bell? Okay, cool. So that was honors third law in whatever that was, 5 minutes. Are we good?
Yep.
Questions before we go on to something more involved? Okay, so in all of those problems that we just looked at, we were looking at just the motion of Roy, or just the motion of Sally, or just the motion of me, or just the motion of the cabinet, right? And they moved independently because they weren't sort of attached, or there was no reason why they had to move at the same velocity, okay? Sometimes, though, we'll have two objects that sort of move as a unit because either one object will be pushing another one, and they'll both be sliding together, or they'll be tied together, or whatever. All right, and in that case, you have to make a free body diagram for a system. All right, we did this last year, but just as a quick reminder. So remember, a system consists of one or more objects. Okay, usually when you say a system, you're assuming at least two, but not always. All right, any force that comes from one of the objects inside the system is called an internal force. All right, and it will not affect the motion of the system. Okay, that'll come out a little bit more in the examples. So hang tight on that. But just remember that any force that comes from within the system is called internal, and it won't affect the motion. All right? So when you draw your free body diagram, here's, I think, what I'm trying to say and not doing a great job of. When you make your free body diagram, you want to draw forces that come from... Wait a minute. Yeah, right. You want to find forces that come from objects that are outside the system. Okay? When you make a free body diagram of a system, you want to identify forces that come from objects that are outside of the system. Okay? And then the net force on your system is the sum of all of those external forces. Okay? Forces between bodies inside a system are called internal forces, and you don't include those on the free body diagram. Cool? All right. All right, so what we're going to end up having to do, similar to what we did last year, if you remember, is you're going to end up having to make multiple free body diagrams. Okay? One for the system, and then one for the individual objects within that system. Okay? Cool. So here we go. So here's, I think I did a couple examples here. Yeah. Okay, so here we go. Example number 3. Let's embiggen this so you can see it a little bit better. All right, so we got a 40-kilogram box of kittens sitting in the center of a frictionless warehouse. All right, Roy wants to move the kittens, but he's allergic to kittens. So he's very sad about it. So instead of just pushing the kittens directly, he finds a 120-kilogram crate full of peanuts, which he's not allergic to. And he uses the box of peanuts to push the kittens. He pushes the box of peanuts with a force of 480 newtons, make a free body diagram for the kittens, the peanuts, and the kitten system. All right, so if you want to process it, here's what's going on. Here's the peanuts, 120 kilograms. Here's the kittens, 40 kilograms. Here's Roy. So there's your drawing of what's going on. All right? So let's go through and make our free body diagrams. I'm going to do them in the order that they're listed there on the page, but they're not really listed in the best order in terms of problem solving. Okay? But let's at least identify the forces that are acting on the object. Oh, I'm sorry, Donna. Okay, so any problems about what's going on so far? Am I going too quick? All right, so the kittens, let's see. So here are the kittens. 40 kilograms. All right. Let's see. Everything here is frictionless, so we don't need to worry about friction. So since Roy's pushing the peanuts, do you agree that the kittens are going to move? Yes. Why? What pushes the kittens forward? The box of peanuts, right? Not Roy. Why not?
Like opposite, because Roy.
Not exactly. Not exactly. I don't want to go there because it's not the same thing. So why is Roy not pushing the kittens? You just said it. We got Nikita. He's not touching the kittens. You can't push a kitten without touching a kitten. Okay? So what's pushing the kittens? The peanuts. So this is the force on the peanuts. And I'm going to, because we're doing third law, let's come up with a normal, like a consistent way to write our forces. So do we want to call this the force of the peanuts pushing the kittens? Is that cool if we use that notation?
Yeah.
Hang on, wait. I'm going to make sure I use the same notation that the... Shoot, you know what? The book uses the other notation. Oh, seriously? All right, so I'm going to use this notation. This means the force on the kittens from the peanuts. I don't either. It's backwards from the way I want to do it, but that's the way the book uses, so I'm going to be consistent. All right. Is everybody good with that? All right, are there any other forces on the kittens? Gravity, normal force. I drew them in red because they're going to cancel and they don't really matter. Take that, gravity. You don't matter. All right. Everybody good? Yep. All right, so there's our kittens. Now, let's make a free body diagram for the peanuts. We'll do that in a different color. So here's the peanuts. Peanuts, 120 kilograms. So once again, there's going to be gravity and normal force that I don't care about because they cancel out. So shout out some forces we do care about. What? Do the peanuts move? Yes. Why? Because Roy is pushing them, right? So this is the force on the peanuts by Roy. All right. Now, are there other forces on the peanuts? Sure, we got box kittens pushing back. Good. If the peanuts are pushing the kittens, then that also means that the kittens are pushing the peanuts, right? So here's the force on the peanuts from the kittens. Okay, and so the idea is because the kittens are in the way, the peanuts are not going to move as fast as they would if the kittens weren't there. Does that make sense? So that's how you should be processing this FPK, is that the peanuts are being pushed back by the kittens, thus slowing down the acceleration they would have otherwise. Follow? All right, and then I think we've got one other thing we need to... Are we missing any forces here? That's it, right? Okay, and then finally, the system. So we'll do the system in green. So I'm going to label this as P plus K, as in I'm identifying that this is the system consisting of the peanuts and the kittens. Okay, what's the mass of the system, you guys? 160 kilograms, right? All right. And what forces are acting on it? Just the force of Roy, right? So here's the force of Roy pushing, what is Roy pushing? I guess he's pushing the peanuts. Oops. I don't know how you want to write this. Yeah, you could either do P plus K, R. I guess it's probably okay to just put PR because the peanuts are in the system and Roy is not. Follow? And I like that because then it forces you to see that these two forces are the same. So let's do that. If you labeled it, if you did what I started to do, change that. This is the force on the peanuts by Roy. And notice the peanuts are part of the system, Roy is not. And thus that is an external force. Good? All right. Do I need to draw the force of the peanuts pushing the kittens?
No, it's inside.
Good. That's an internal force. So I don't need to worry about the force of the peanuts pushing the kittens or the force of the kittens pushing the peanuts because those are both internal forces. Does that make sense? Yeah. All right. We do need to include gravity because that's an external force because gravity comes from the Earth and normal force, right? Okay, are there any other forces? I think that's it, right? Okay, so those are my three free body diagrams. Wow, say that 4 times fast. I'm going to erase this just to make some room. Okay. All right. We only know one of these forces. What's the only force we know? We know the force of Roy pushing the peanuts, right? What was it? Was it 480?
Yeah.
All right. And so now we need to fill in the rest of the free body diagram. Remember, when I ask you for a free body diagram, implicit in that request is also find the net force and the acceleration. Okay? So, which of these three free body diagrams is going to help me the most?
System?
The bottom one, right? Okay, the top one doesn't help me because I don't know how much force the peanuts are putting on the kittens. And the middle one doesn't help me because I don't know how much force the kittens are putting on the peanuts. But the bottom one is actually useful, right? Any questions? So, here we go. Peanuts plus kittens. Acceleration is net force over mass. So what's the net force on the peanut kitten system? 480 newtons. What is the mass of the peanut kitten system? 160 kilograms. Divide it out and you get 3 meters per second squared. Does that make sense?
Yes.
All right. So,
Scary looking.
what do I know about the acceleration of the peanuts and the acceleration of the kittens?
They're the same.
They're the same as the acceleration of the system, right? Because they're all sliding together, right? Okay, so now I can do this. Let's look at the kittens. The acceleration is 3 meters a second squared. So what can I find? Net force, right? So the net force on the kittens is ma, mass of kittens times acceleration of kittens, which is, 40 kilograms times 3 meters a second squared gives me 120 newtons. Follow? So what can I do now about my drawings over here? I know that this force here has to be 120 newtons, right? Because if the net force is 120, and the only force affecting the motion is the peanuts pushing the kittens, then this force must be 120 newtons. Cool? How come I chose the kittens instead of the peanuts when I made that Freebody diagram? Doesn't really matter, but anybody see why I chose that one? Yeah, there's more forces on the peanuts, so that drawing is going to be a little bit more complicated, right? All right, are there any questions so far? All right, and often what you can do when you get to this point is you can use this information to check your work. Because look, if the force of the peanuts pushing the kittens is 120, then this force has to be negative 120, right? The force of the kittens pushing the peanuts. Follow? If you're dyslexic, this chapter is going to be your worst nightmare, and I'm sorry in advance. All right, are we good?
Yeah.
All right, so now we can kind of check. So let's look at the peanuts and the kitten system. No, not at all. That's not what I want to do. Sorry. Let's look at the kittens. We've already looked at the peanuts and the kittens. Who wrote this problem? Jeez. All right. So here we go. 120 kilograms. We know that we've got the force of on the peanuts by Roy.
The peanut system.
We got the force on the peanuts by the kittens. All right. What can I do now, you guys?
Track that before.
Find the net force on the kittens. What are we going to get, you guys?
360. It should be the peanut system, Mr. Riker, not the kitten system.
Oh, I'm sorry. I wrote. Oh, shoot. Yeah, thank you. Peanut system. Sorry. Thank you. Peanut system. Sorry. Everybody back on board?
Yes.
Am I going too quick? Are we good?
We're solid.
All right. So the net force on the peanuts turns out to be 360 newtons. So what's the last thing I should do?
5 by 125.
Find the acceleration and make sure you get the same answer, right?
Yep.
So net force over mass. So we had a net force of 360 newtons acting on 120 kilograms of peanuts, and you get 3 meters a second squared, and thus we are happy. Cool? Sorry? Oh, correct. No, yes, no kittens were harmed in the making of this example. Exactly. All right. Everybody good? What I didn't tell you guys is that kittens are allergic to peanuts. Totally joking. All right. Okay. So there are two other types of examples that I want to make sure that we tackle. There are two other types of examples I want to make sure we tackle. Unfortunately, we've only got time for one of them today. All right. So the one I want to do today is sometimes one object will push another object. This we did not do last year, so this is new. Sometimes one object will push another object by virtue of the friction between them.
What?
Like, for example, if I pull this thing, then the cabinet just pulls my coffee mug forward because there's friction between them, right?
Oh, that's
Okay. All right. So I'm going to do that, and then the other thing we got to do is sort of these generic examples with no numbers. All right, because those I know you guys have a tough time with those. So the one we're going to do today is the friction one, and then I wrote one with no numbers to go over on Wednesday. Okay. So what did I write up on the board up there? I can't see it. What? So yeah. So let's make since you guys have tomorrow off. Sorry, I know. Let's make the 5-1 stuff due tomorrow, and that way. Do Wednesday, yeah. And then, yeah, so that's the deal. All right, so here we go. All right, so this time it says repeat the last problem, but this time let's assume the 40-kilogram box of kittens sits on top of the peanuts.
disaster.
I think we'll be okay. All right, so it says suppose the coefficients of static and kinetic friction between the kittens and the peanuts are 0.4 and 0.3 respectively. So here we go. Let's make a quick drawing so we can kind of process what's going on. Here's the peanuts, 120 kilograms. Here's the kittens, 40 kilograms. Here's Roy. Oh, it doesn't tell us how hard he's pushing. Okay, hey guys, I realized the way I wrote this is a little misleading. It says to repeat the last problem. Let's not assume we know Roy's force, okay? So we're repeating it in the sense that he's still trying to move the kittens, but we don't know how much force he's exerting. All right, so there's our drawing. All right, so question number 1 says, what's the maximum acceleration he could give the crates without the kittens slipping? All right, so to answer this, let's do the same thing we did last time. Let's make 3 free body diagrams. All right, I usually find that it is easiest to do the one for the system first. Okay, so let's do that. All right, I know that's not what I did last time, but I think that's easiest. All right, so here we go. So here is the peanut and kitten system. It's 160 kilograms. The warehouse floor is still frictionless, so the only friction now is between the 2 crates, to be clear. Okay, so here's our force of Roy, and then once again there's FG and FN. All right, so there's my system. Good? All right, so now we got to do 2 other free body diagrams. We got to do one for the kittens and one for the peanuts. Which one do you want to do first? Kittens? All right. I don't know why I said that like that. That was what I was hoping you would say. The kittens one is a little bit simpler. So here's my kittens. They have a mass of 40 kilograms. So right away I know there's going to be a force of gravity, which I'm actually going to find. It's 392 newtons. And a normal force of 392 newtons. And what? Friction. Between the kittens and the peanuts, right? Okay, so assuming that the kittens do not slide across the top of the peanut box, in which direction will the force of friction act? I see people pointing 2 different directions. Roy is pushing the boxes forward. So if we assume all right, so here's my box of peanuts. Here's my box of kittens. These are kittens. All right, you ready? All right, which direction did the kittens accelerate in? This way, right? What caused them to accelerate? Not Roy. Roy didn't touch the kittens. Friction. All right, the static friction pushes it this way, right? Because what if... I thought you guys were going to clean my desk for me. What would happen if there was no friction? Oh, shoot, it's not level. All right, so watch what happens. There's no friction now. Watch the little cart. Right? It stayed right in front of Zach. It didn't move, right? Because there was no friction. Does that make sense, you guys? All right? So which direction is friction acting in? To the right. Force of friction, static max, right? Because we're trying to find the maximum acceleration, so we're going to maximize our static friction. Now, to be clear, let's describe that in an alternative fashion. That doesn't associate it between 2 objects. Every force has 2 objects associated with it. So this is really the force of what pushing or pulling what? Friction's not an object. It's the peanuts pushing the kittens, right?
Yeah.
Okay, so it's the force on the kittens by the peanuts. Does that make sense?
Yep.
Oh, and we can actually calculate that, can't we? FFS max is our coefficient of static friction times our normal force. So our coefficient of static friction was 0.4. Our normal force is 392. Multiply this out, and you get a number that I don't remember off the top of my head, but somebody conveniently left a calculator. What do you got? 156.8. Thank you. So let me pause there for a minute. Does that make sense? All right. Oh, so I can find the acceleration of the kittens, right? So 156.8 newtons divided by 40 kilograms. And it gives you, what, 3.92 meters a second squared? Is that right?
Yeah.
All right, any questions? We're almost done. When does the bell ring?
In a minute.
Is it 09 or 15?
It's all nice.
I'm going to waste time figuring out when the bell rings.
You have 1 minute.
All right. Okay. So at this point, we can. So now we know. Now we know the force that the peanuts push the kittens with. So when I draw the other free body diagram, what do I know?
The force of the kittens on the peanuts.
Yes. All right. So. Well. Oh yeah. Oh no, you can't. Shoot. Dang it! I wish we had 5 more minutes.
I know how to do it. I know how to do it.
All right, I'll tell you what, let me do this. Instead of finishing 5-1 for tomorrow, see if you can finish this example for Wednesday. All right? That's like the biggest gift you ever do to you. All right? Just finish this for Monday. See if you can do it. If you can, cool. If not, we'll talk about it. All right?
I just figured
For Wednesday.